新生是什么啊？这 Hello. Okay. Good morning to everyone. Have you guys finished your midterm season yet? No. Huh? Haven't started? Wow, you're so lucky. So when's your final midterm? Weekend. Weekend. Huh? Weekend. Oh, okay. Quite late. Okay. Right. Um. Yeah. So I have updated tutorial question solution here. So I've added tutorial 4 and 5. Okay. So if you at least don't have time to do right, please read it. For examples, in this tutorial 4, right, I have this question here. Okay, so if you can define your affine, not affine variety, but algebraic set, okay, using this parametric equation here, then it is actually irreducible. So basically, these are the object that you're looking at in calculus 2, right? That you can parameterize them. Okay, so actually they have to be irreducible. Okay, so that's why when you sketch them, it's like one piece. Okay, one piece. Okay. Yeah, so if you can see that here actually uses what called the elimination ideal here. It's quite similar to your assignment question, right? So basically when I set these assignment question and tutorial question, right, usually I set them together. Okay, so that you can do the tutorial first. Okay, try the tutorial first. And then you can do the assignment better. Okay. If you jump straight away to assignment, also no problem. Yeah, but just that you might be harder for you. Yeah, because so you notice right, like Adrian said, right, why your assignment harder than the others? Others one I do like few hours I finish already. This one not from you, on others you. Right. So the point of my assignments, right, is not to repeat what I've done. Okay. The point of my assignment is to let you use whatever I told you. Okay, to do something else. I to apply. Okay, apply in real world situation, research problem, or something like that. Okay, it's not just I teach you one, you write one. I teach you two, you write two, or at best you write three. No, you should be able to write 100,000. Okay, I don't know you see a meme before or not about what teacher teach in class, what you do in assignment, and versus what you do in class. Huh? Why? Yeah. Okay. Uh-huh. Oh, yeah. But that's very true actually. When I was you, I also don't understand. I don't understand. Why so hard? Hey, this one teacher no teach me. But if you think carefully, the backbone is what is learned in lecture. And what you need to do is more than the backbone. It's not just the backbone. Okay. Yeah. Right. Something useful for this tutorial stuff. Okay. So if you look at tutorial 5, first question here, right? Actually, this is the key you use to prove Hilbert's non-standard. Okay, so actually this is the real accent of Hilbert non-standard here. So what's this accent here? So it says that if you want to check that whether F is radical or not, you just need to check whether one lives in this larger ideal or not. Okay, this is an if and only if condition here. Basically, this is what we use to check Hilbert non-standard. But Hilbert non-standard only have one direction. This one has the other direction. And actually, the other direction is not difficult. It just relies on you how to write one in the form of power of n. Okay. And then question 2 actually is what we mentioned in class. And then I just ask you to write it up here. But 3 is quite interesting here. What did you see here? You see a bit of analysis here. And partial derivative. Huh? What? So, polynomial? Uh-huh. Why are you trying to say? Yeah. Let's close the door. Okay, so if you read at this question here, right? So if you know that your ideal is a principal ideal, you want to ask what's the radical then? Okay, the radical is generated by how many elements? Actually, also one element, but what's the element that you're generating? So basically, you just get f and then divided by the GCD, okay, of all these first partial derivative with f. Okay, yeah. So it's quite interesting, yeah. And in the proof, right, actually tells you what's the this GCD here. Not that this proof only works for what? But for a field that contain rational. Okay, if you are characteristic finite field, then it might not works. In particular, that formula there. So from previous question, right? This is the another incarnation of these see, the incarnation of this irreducible factor here. Okay, you can read it as f the something extra there. You can read it as the greatest common divisor of all these. And actually, this is something that play a role in your in the next maybe in the next coming up section, which is about singularity. Yeah, these first partial derivative. And then this is some very usual routine exercise here. This one, without knowing what it is saying, you should be able to use definition to work it there with power of function here, right? Because what's radical? Something. What's radical of an idea? What? Say that. So radical of I is all the functions such that to some power of that function is giving it back. So meaning you are taking a power of root of that function and power of root. Okay. Okay. So the square root there doesn't just refer to power 2, it's refer to all the positive power. Okay, you can. Yeah, and then lastly, this closure of I is something that corresponds to Zariski closure of your algebraic set. Okay, so this is a dual element, dual object from Zariski closure. Okay, so this one is a closure. So here there's a might be a new word for you that we rarely taught in class here is the ideal of a set of points. Okay, ideal of a set of points here means what? For example, what's not an ideal of a set of points here? So last time in class, right, we checked that the ideal x squared, ideal generated by x squared contain ideal x, right? Ideal generated by x. Okay. But we call it ideal generated by. So what's the zero set of both of these? Both are zero, right? Okay. But we won't call ideal generated by x squared ideal of a set of point of zero because we found a smaller, not smaller one, the how to say this. How to say this? Okay, let's give another example first. For example, ideal generated by x squared plus 1. Okay, this is not an ideal of point in real number. It's an ideal. It's not an ideal of a set of point in real number because there's no real solution. Okay. Okay, so the sun solidity here you need to okay. Does it make sense or not? Does it make sense? Does it make sense? Idea of a set of points. So usually what is in the idea of a set of points? Last time we say that okay, if it's just finite set, let's say if it's finite set, then it's the maximum ideal generated by the factor of xi minus ai. Okay. Or intersection intersection? No, it's a union of these function. All the intersection, no intersection, but you have to be union of these any question about this one? Or you try first? And if you have problems, like you come from union. Okay, let's continue. Okay, so I think I owe you something, right? I haven't give back your assignment 2, assignment 3 just finished, right? Okay, so if you have any delay or extension, make sure you send me email or message me, because I need to keep a record there. And then um so I think because my family left last Saturday, so they gone back already. So I think I can have full time doing again. So hopefully I will finish by either this week or next week about your assignments, and then I will definitely come up with your new assignment this week, yeah, and then tutorial together. Okay. Yeah, sorry, where's the deadline? Okay, so my deadline is usually I set around 1 week plus, 1 week and a half like that, or 2 weeks, something like that. 1 week and a half like that. Yeah. So count from when I posted 1.5 week like that. Okay. So when I gave you 1.5 week, right, make sure you really spend 1.5 week thinking about it. Otherwise, you are forcing yourself. Okay. So my assignment is not for you to do it 2 weeks, 1 day, 2 hours like that. No. Okay, you need to think about it. Um, so this is assignment, this is tutorial. Okay, so what's the plan for the towards the end? I think how many weeks we still have? We still have 6 weeks, not including this week. Okay, so in this 6 week, right? If can ideally, ambitiously, if can we cover 3 new sub topic. If not, we'll cover only 2. Okay. Um, and then how about your presentation? For the leaders here, who haven't gave me your subtopics yet, please post to the group. So 1, 2, 3. Who else? Who's the leader here again? 1, 2. Joel gave me already. 3. You got 4. Another one. Who's the another group? Who are? 2. Oh, right. That guy. Where is it? How Tian? Where's How Tian? What? You don't know? He informed you or what? Don't know. Just that haven't appeared. Last class also. Okay. Gang gang. Oh, okay. Is it traffic jam? Yeah. Yes, roadblock. Asian Summit. Okay. Um, what else I need to? Any question about this course or not? Any other question? Okay. So the final, right, I'm applying for you to bring a piece of cheat sheet. So I will wait until the confirmation. I'll let you know. Okay. More one cannot. No. So So I guess the difficulty also restrict to one cheat sheet is enough. That's it. That's the story. Okay. Yeah. So about my usual midterm method. Okay. Yeah, because notebook is a bit hard for me to keep track later, unless I got a uniform notebook. Next time when I got more budget, then we can do that. Sorry? No, A4, A4, A4. Okay. Yeah. Then I'll tell you what's the scope of the exam. I don't plan to include everything actually, so I'll let you know again what's the thing that included in the exam scope. Okay. So this week, hopefully, we have to finish projective variety pretty quickly. Yeah, because projective variety is actually another story of affine varieties. But actually do better than affine variety. Soon you will see that how we can view an affine variety as a projective variety or quasi-projective variety. Okay. So in that sense, projective variety will be a more general variety that you can talk. Okay, so these 2 days, right, we will repeat on Cuban Nautilus again. So it's a projective version, and then dominant maps, regular maps, again on quasi-projective varieties. So we'll do pretty quickly, and then we'll tell you what's the difference. Yeah, what's the difference between doing in the affine setting and a projective setting? Okay. Okay, so let's remind us what's the thing that we did last time. Okay, what's the thing that we did last time? So last time we defined a subset of Pn, okay, to be a projective algebraic set if there exists a subset theta of homogeneous polynomial in S such that y is equals to zt theta. Okay, so what's the zt theta here? Where zt theta is referring to the set of zero. Okay, set of zero such that fx naught n is equal to 0 for all f in T. Okay, so these are the point in P. Okay, so you can see that this definition actually not much different from the R5 version, except where. Okay, what's the differences here? Okay, what are the differences here? For example, we pick the point from a projective space now instead of affine space. And then the polynomial we consider here is just homogeneous. This is what we shown you last time, right? Okay, to make sure the whole line live inside the zero set, we need to somehow homogeneous it. Okay, although I haven't defined what is it. If we don't do in class, I will at least do it in the project. So this is the difference between affine set and affine algebraic set and a projective algebraic set here. Yes. Um, so we call it Sn last time, right? Sn. Yeah. So basically, we purposely discount the S naught. So that's why we start our S1 with S naught for the function ring for the space here. So you can see that it's really similar here. So we also name it algebraic set. Okay, so you can see that actually later these algebraic set will follow the same structure that you have on alpha algebraic set. For example, what? The union of algebraic set, the intersection of algebraic set, what is it? Okay, you can write it as another algebraic set. Okay, so you should think that, oh, here we also have a Zariski topology here. Okay, so this is what is hinting later. So really, it's not too far away, okay, from what you have from alpha and algebraic set here. In fact, later we'll see what's the difference, okay, between them. What's the slight difference between other? So what's the slight difference occur when you regard this Pn here? But what's the difference between Pn and An? Can you tell me from what we have learned on the first 3 weeks? What's the difference between Pn and An? Jack? Hmm? Sure, you can talk about Pn and Am plus 1. What's the difference between them? Yeah, what's the difference? Must be different, right? Otherwise, why I given a different name? What's the difference? What's the difference? This is very key important to answer, to understand all these theory. And then Pn also have, right? Also have n plus 1 coordinate, right? But what's the way of writing an element in Pn? Huh? I mean, what's the different way of writing the n plus 1 tuple there? One you use comma, the other one you use semicolon. But why you use semicolon? Because you treat it as a line instead of a point in an plus 1. Other than treating an plus 1 as a line for Pn, right? What else is the difference? Remember where we take the equivalent class? We didn't consider the 0 point. Okay, we throw away the 0 point. Okay, so these two make out the differences between these two spaces. Okay, so please bear in mind this important property. Okay, so what are the examples here? So let's quickly go to some examples here. So first example is the hyperplane at infinity. So what is it here? So let me define for you. So these are hash n or the point such that one of the coordinate is 0. And so this is a projective subvariety. Last time we looked at an cover, right? Okay, such that one of the coordinate is non-zero. Okay, the cover of a variety. Second, you can have this variety here. Maybe you can go back and try and draw it. Not sure you can use maybe ask ChatGPT. I recently found that ChatGPT is a very nice thing to use actually. It's a logic. It's very good. Yeah, logic is very good. I'm not sure about computational wise, but the logic is really good. It's not good when deal with my assignment. Yeah. Okay, I never asked him about my assignment yet. Maybe next time you should try. Okay, I think sure I'll do it next time. But what I want to say is really logical. More than logical, actually, he will ask you to follow up. He will try to give you a plan. Okay, how to continue, how to improve, or how to design something that you want. Or it's very, how to say, organized actually. I think organized is more organized than most of the lecturer. Yeah. Yeah, it's really better. I think it's a very good, how to say, 舞蹈怎样讲啊？英文忘记了。舞蹈员 counselor, yeah, it's a very good counselor actually. Yeah. So if you have any confusion or any how to say if you met any difficulty you can try and ask ChatGPT. Your ChatGPT won't store you one, huh? Xiaomi is one of them. It's very trendy now. It's very trendy. Yeah, it's come out in the news, so you can go and try. The other thing is, yeah, it's a very good counselor. He won't score you one. He won't score you. He'll try to how to say make use of whatever your good or your bad. They will like suggest the best way for you. Okay, no? Yeah. Okay. So can you see that this is a projective variety here? So can you, in other words, can you recognize that this is a homogeneous function here? Then what's the degree here? Degree 3, right? Okay, so you can see that each monomial has the homogeneous degree 3. Okay, another one. Yeah, let's define it using a parametric equation this time. Maybe I let you stare for long a bit on this parametric equation here. Can you recognize that what homogeneous polynomial it satisfies? Can you think of any homogeneous polynomial that is satisfied b equal to 0? I mean the image. Huh? X plus y cube. So you treat. Okay, let's give these coordinates some name. So there are 4 of them, right? Let's call it x0, x1, x2. You cook up any homogeneous equation such as 0 based on this image here. Guess. Maybe you don't just need one, no? Maybe you need more than one here. Guys, x, x naught, x2, x3, and then s naught, s2, s naught, s3 minus x1, x2, and that equals 0. Okay. This is one of the equation is satisfied. Actually, there are 2 more. There are 2 more. Maybe I give you one, you can guess one more. X naught, x2 minus x1 squared. Can you guess another one? Yes. Okay. So basically, let's call this C, right? Okay, let's call this C here. So let's call it C. C to be the image of this file P1K here. And then actually this C, right, is the intersection of these 3 pieces here. Okay, so these 3 pieces here is made up by the 0 set of these 3 equations. So I'll repeat it. So all together, right? Actually, we have a more sophisticated way to talk about this. These are all the points in E3, E3, such that the rank of this particular rank of this particular matrix here, x0, x1, x2, and x1, x2, x3 is less than 1. Okay. So this is like a minor, right? So these are the minor of this matrix, right? You see, they are the minor. Oh, so what's the minor? What's the minor? Adrian. Yeah, yeah. So in this case here, if you remove the any column, right, then you compute the determinant is either one of these. So if you remove the first column, right, you get x1, s3 minus x2 squared. So on. Okay. Yeah, so if you want to make sure your rank is less than or equal to 1, then you need to make sure all these minor is 0. Okay, this is a linear algebra. Okay. Hey, I found that in your DG class you also do this kind of things. Are you guys doing this kind of things or not? I saw one of your question is checking something is the quadratic surface. How do you check? Satisfy some polynomial equation. Correct. I thought this one is in my class. Huh? That's why you say. Yeah, that's right. Okay. Okay. Sure. So you can see that this is intersection of 3 quadrates here, right? Because these are degree 2. So this here. Okay. The fourth one, a bit advanced a bit. There's an example here. Also first time seeing it. So if you look at this product space here, we haven't formally defined the product of a projective variety, but I'm going to use it first. So you just think of a set product first before endowed it with universal property. So basically what I do here is I regard this image in P3 again. Let's give it some name first. So Z0, Z1, Z2, Z3 here. Okay. So can you guess again what's the equation you have to satisfy? Yeah. Maybe I give you some hint that this is a quadrate again. So it's homogeneous of degree 2. Ah, Z1, Z2. Good. Z1, Z2 minus Z0, Z3. Then equals 0. Okay. So what's this picture here? Well, very interesting. This picture here. Actually, there are two family of line that satisfy uh, this equation here. This picture actually looks like this. Let me show you. Okay, so if you plot out the zero set, right, of this Q here, there are two family of line kind of like transversal to each other. Okay, transversal to each other. I'm not sure it's 90 degree or not. Maybe it's not 90 degree, but it's transversal to each other. Transversal means it's not like touching like a tangent like that. Okay, this is not transversal. That's why it must like cut through it. Okay, there are two family of lines like that. They call it rulings in this case. Actually, I think you need to really follow or find the zero set so that you can know this. But how to prove it, I'm not sure yet. Yes, model figure. So if you go and find the zero set of this quadrant here, okay, we have found that there are two family of lines. Okay, so what does this two family of line do is this two family will intersect with each other transversally. Okay, it's not like tangentially, yeah, so it must cut through like that. And then within the family is like a parallel to each other. Oh, okay. Actually, I think this is infinite. It's just some portion of it. Mm. Can I? Sorry. 这个图说说看。Well, I mean, let me see how to talk about it. So this is supposed to be infinite. Yeah, supposed to be infinite. So yeah, infinite. Yeah, yeah. What's wrong? It's okay. Okay. No. You got problem. You ask that. You ask. What do you mean? I mean, it's like what do you mean you don't understand? I don't know why you don't understand. You don't tell me. Yeah, I guess it's just a portion of it. Okay, so maybe okay. If I want to say, I think it's like family of line around cone, a cone, huh? A cone. So you are like, so you got a cone, right? Infinite cone. So these are the point on this cone. Round the naked cone. What do you mean by round? Round, there's a lot of way to round, right? So it's like just a line on that cone, the face of the cone. The cone. Yeah. The face. Yeah. Does it make sense? Good. That's fine. Yeah. I think you can think of it like that. Yeah, you can think of it like that. Yeah. You can think of it like that. Yes. If I don't understand, then you have to speak English. Ah, in a projective space, and then you see that line will actually form. So the cone might not look like a circle, but it will be a cone with a very unique shape. But going through the origin, you study, you will still form. I think you will miss the origin. Yeah, no, there's no origin. You will miss the origin. Yeah, it's just around the origin. Okay. Uh, yeah. Maybe you can try figure out why this is true. Yeah, I'm just collecting some examples here. I believe it's just from plotting the zero set, but to prove why is it like that, I have no idea yet. If I found it, I'll let you know. If you found it, please let me know. But for now, I just want to focus on this part here. Okay, how to find these homogeneous function. Okay. So similarly, like affine case, we have these polynomial ring of n variable to govern these varieties, right? But how about projective varieties? Okay, so here we will introduce something called the graded rings. Okay, and also homogeneous ideal that we have briefly talked about last week. I mean, last week we just talked about homogeneous degree, huh? Okay, this week we'll talk about homogeneous ideal. Okay, so let's start with a graded ring here. So here, a graded ring seriously just a ring, but there's an adjective now, it's graded. Okay, so what does it mean by graded? How do you mean by graded? You are living in a graded class, right? Graded education. Each semester you get a grade, right? Where someone get distinction, someone get what? What else? I forgot what's the other grade. Yeah, distinction. Okay. So a graded ring is a ring. Okay, first of all, and you must be able to decompose it into a billion group. Okay, into a billion group. So when we say about a billion group here, this is the group structure of rings. Okay, so what do we mean here? So we will write it as a direct sum, okay, of some component we call xd here. We call it d component, but we index d from 0 to infinity. So what does it mean by direct sum here? So let's define it here. So such that, okay, for different pieces of d component here, okay, let's call this d component. Thanks. So for different d and e here, their intersection should be empty. Not empty, empty other than the zero element here. Later you will know why this zero is in every set here. And such that if you do xd times xe, so meaning you take the d level of elements here, multiply by e level here, you will go into a d plus e level. Okay. Don't confuse with the group addition group structure of the ring on d plus e. And d plus e here is really just addition of number of positive integer. Okay, and then the elements of xd are called the homogeneous elements of degree d. Okay, up to here, any question on this definition or not? Up to here. Hang Wei, what do you think about this definition? Any part you're confused? Okay, so dot here means what? So if I take something from this SD, right? So X, and then we take something from this SE, right? Okay, because they are elements in the ring, right? We're supposed to be able to multiply them together. So S dot Y will live inside X dot SD plus E. Okay. So you go to a higher level. Yeah, so such that here is defining this direct sum. Okay, so direct sum here just says that. Oh, okay. Maybe we left off one more thing about direct sum here. So we have that xd intercept xd is 0, and then okay, maybe one more thing we can add here. For every x in S, x equals to x1. So let me put x0 plus x1 plus blah, 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 up to some xm where okay, I cannot do like this, so let me write this. So x is equal to x of I0, I1, okay, I1 plus up to, let's say, In, where xi1, xij come from sj. And this n should be finite also. Okay, so basically it means there is a finite sum. Okay, finite sum of elements here. S can be written as an element in S can be written as a finite sum of homogeneous element of degree E. Okay, and then the intersection being 0 here will imply that this sum should be unique. Never see this kind of direct sum before. Linear algebra didn't do this direct sum, no. Okay, I'll let Ali know. Okay, any more questions on this direct sum property here? Yeah, to each index. Okay, so why I add one more? Can you recognize why? Can you recognize why? Because maybe your sum might become from different xi, right? It might not start from x1, right? It might be a random xi.
But it can be zero, right?
Can be zero, can be zero.
So
what's one?
I don't think you need to add one more index.
Oh, okay. So okay, maybe this is a preference of case. So what does it mean? So if there is nothing from that homogeneous degree, maybe you can replace it by zero. Okay. Like maybe you don't understand what I say. So maybe something like this. So okay, what I thinking here is I'm picking the let's say the non-zero element here. So let's say x1, let's say x0, x1. Maybe you have some zero here, and then x2 plus, so here maybe s3, s4 plus 0. And then maybe plus until s6 like that. Okay. Why I do that is just now what I'm thinking. What's my thinking process just now? So what I was thinking is I just thought of these. I didn't think of the zero. But if you think of the zero, you also can stop at a certain end. So in that case, and then they will follow what Eric said just now. You don't need to re-index it. Huh?
Exactly. Sij should only be Sij, otherwise your index is no room.
Huh?
In your way, the little Sij should be bigger Sij, otherwise what you are writing is just what I'm saying, but the double index implies.
Oh yeah, right. Okay. So so how should I do it? So maybe just follow what you say. So let's try it. Excellent. Okay. So previously I thought I want to throw away the zero, but never mind. If it's zero in the sum, is that's fine. Can you recognize why zero is in all the intersection? Sorry? Huh?
Yeah.
Yeah, abelian group. Yeah, abelian group. Oh yeah, right. Yeah, that's one of the reasons. Yes, very good. Yeah. So because we split it into a abelian group, So it should contain these common 0 here. But we only require it to contain this 0 here. Okay. And then actually this intersection also compatible with our multiplication definition here. Also compatible. Because everything you multiply to 0 is 0. If 0 doesn't live in SD plus E, and then your multiplication also, the subtrate equation will go problem also. Does it make sense? Does it make sense? If you take anything in SD multiplied by 0, let's say x equals 0, then you get 0. So you need to ask yourself whether this 0 live in SD plus E or not. If it doesn't live in there, then that is not compatible with the script. Okay, so so one proposition here is the polynomial homogeneous of degree D from a subspace. Okay, so subspace meaning if you add a homogeneous degree element together, right, of the same degree, you still get a homogeneous degree D element. And you still can recall what's the polynomial of homogeneous degree D means or not? What does it mean? Yeah. Yeah, so if you look at every monomial term, right, the total degree should be D. Sometimes we call it total degree, sometimes we just call it degree only. Okay. Yeah. So as a degree of a monomial, then you just add up all the power of these um, variable, okay, or the intermediate. Then actually you realize that the whole ring, okay, can be written as a direct sum of these homogeneous subspace. Okay, so repeat again, what does the direct sum means here? So whatever we written there just now, right, it implies that every element inside this coordinate ring here can be written uniquely as the sum of fi, where fi live in the in this case we label it as I subspace here, homogeneous degree I subspace. Okay, for some I. So there's a very important point here. Although our direct sum go infinite, right? But the elements here is really a finite sum. Stop at a certain end. Okay. Stop at a certain. Okay. Can you imagine this or not? Is it true? Is it true or not? So can you give me some element inside this coordinate ring or not? K1, X0, X1, dot out to Xn. Maybe we don't prove it. You can write it down. So let's look at the example. For example, what are the elements inside there? Huh? What's the element inside this ring here? Can you give me some elements here? Levy, is some nice one. You are my ChatGPT now. Please give me a nice element inside here to illustrate this proposition. One. some polynomial so that I can use it to explain this.
X1, X2. Plus 4x4 cube.
X4 cube. Done? Done. Okay. So let me revise a bit. So let me add x1, 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 x2. Okay. So in that case, in the context of this theorem, how do we understand this polynomial then? Right, in this context, how do we understand this polynomial? How do we view this polynomial inside this direct sum here? How do I split it? How do we split it? Inside the direct sum, the keyword is what? Homogeneous of degree D. So where's the homogeneous degree here that we need to consider? Which degree we need to consider? 0, 1, 2, 3. Good. So we got a 0 here. So degree 0. Degree 1. Degree 2. And degree 3. Yeah, so you can see that there's non-degree 2 elements, right, other than 0 can live in the other degree. Because we count by power of the variable. And the total degree. I mean the degree of the polynomial. Yeah. Okay. So in other words, for example, if I take degree 0, if I take degree 0 element, I multiply with a degree 2 element. What do I get here? You did get a degree 3 element. So it's actually, so here let's say this is x1, right? x1 in using the just now notation, x1, x2, it should live in s3. Okay, make sense? Okay, no? Okay. Okay, so this should be how you view a polynomial right now. Okay, so split it into homogeneous of degree D. Okay. Okay. I think this is also what you do, right? When you started to do maths, you put your order in sequence, right? Small to big or big to small. Okay, and then each of them will live in a different subspace. Okay. When I say live inside a different subspace, you are using abelian group structure. So any. Okay, so okay, let me show you another operation. So if you take 4x cubed, right, plus x naught, x1, x2, they are still in S3. Okay, so inform a subspace in the definition. Okay, any question? Notation 稍微什么？ like S3 symmetry function. Only oh. You mean this part don't use X? I mean, in this part, I'm just in class. I write like this, but I mean, if I write it, yeah. If I need, I think I will write like this. So okay. Maybe in this case, let's stop at x2 to x4 in this case, and then this is in the degree, right? So we put it here, 3. Like this. Okay. Any question? No? Okay. So the idea of grader is pretty important. in a very advanced math, we always want to grade our objects. Yeah, we want to have a grading there, and most calculation actually follow grading. So if you look at here, right, the multiplication, right, somehow compatible with this grading here, and then addition, you will stay in the same grading. Multiplication, you move up in the grading. Okay, make sense? Okay, okay, let's take a break until 111. What?
你这个底是
啊，是吗？
他们有连一个零，需要一个有连一个零。
讲 high variety 那是他讲 algorithm
零，可是我们这边 form subspace 过后就在里面了，谁没有把零放里面？有人没有把零放里面？我没有看过，但是至少这边讲 subspace，所以零应该一定要给。
我看到有一个写法，就是这个底是写在上面，然后他们有连一个零啊，可是应该跟你这个也不应该一样。
你给我看一下，
我
你下次给我看一下。哦，有，也有这个 notation。这个 notation 我现在没有介绍，只是我 lecture 懂吧？也反正 like I mean
应该
一样，因为它 subspace。
对。
啊。
然后这些东西，然后去做 dimension algorithm，结果做不到，然后找很多，找几个小时，然后找到一个东西叫做 monomial ordering，这个东西跟 group 那边是有关。
对。
然后再给我看就很多 drop 的 base
哪一个第三节？
把三分中间，
有关。
我先说我其实后来发现有个 bug，但是这个 bug 留着你去发现。
你不要发现写给我看，我这边有 bug。
我发现我有 bug，但是我想让你去找我的 bug。
喂，不要给我功课好不好？
你都能
等下扣很多分哦，你给我功课。
别
你要不给我承认老师。
那你自己去读嘛，我就跟你说，其实整个逻辑我们就有一个地方不同，我就想让你去刷。
但就是不同了，你还跟我讲整个逻辑不同了，就学数学而已。
然后我在怀疑有 monomial ordering，这样怎么关乎那么出来？
其实那个 monomial ordering 不重要吧？
因为没有的话，我真的是总结不到我的 remainder 的比小于我的，
就也没有，我觉得 ordering 没有什么重要吧，就是你自己定你要 divide 的一个顺序就好了，不用这么 for。
因为我有 kx 然后我把 kx 当成coefficient，我控制了 y 的零，我控制了 kx 的零。
然后
我要是在 kx join y 除的话，我只能总结我的 degree in 它的 y 会小于它。
OK， 然后
那加上那 coefficient 不一定了，因为我要想保证我的一个 kx 就是它的 coefficient。做不了。
那你做到哪里啊？
那我结果没有做。
哦，没有讲你做到哪里啊？做销的那一步了。
有吧？
做到哪里啊？没有印象。
那真 not make sure 的 idea 是 generated by 一个 input program。然后正常一点，你可以是 assume 一个 minimal degree 的 epsilon。你 show that irreducible， 然后你 show that 它的 generate 这个，完全用 division。
哦，你要 prove 它 irreducible， 然后
irreducible 没有问题 ，prove 它要 prove 它真的是能 generate 那个我要的 idea， 没有问题。
哦，你是要 prove principal idea 还是什么？
principal idea？
你 principal idea？ 哦，然后你要 show that remainder 是零，不懂啊，我现在想不到，你问一下他们是这样做。
我还没有跟你的，
我有给 hit 没？
有
啊哈，你现在是讲第三不是？还是第？哦，你是讲第一？哦，你讲那天我给的 hint
但是我
没有诶，不需要诶。
我
哦
我能不能的，我就自己
哦，叫你 try 啊，而且也没有什么 ordering 啊，不是两个 coordinate 罢了，两个 coordinate 罢了哦。有什么？
你要来除好麻烦。
你可以 isomorphic 去那个 KXY 像你讲啊，然后你就先做了。
你肯定是那里面有啊，
然后你要做，一直做除法的。如果是做法简单的话，这样你会我是就从来没看出来出来看到
那有几千，不累吗？说要不累？
一个一个把人扫一下。在这个部分，可以吗？
哦，这个我在想应该是这样子，我不知道，我不知道，这个我不知道。对，想着为什么还是我怎么知道后面没有更多？
对啊，我也想问这个问题。
啊什么？
答案
嗯，
对，为什么还没有更多一个 section？
他想问为什么只有这三个东西没有人？
啊，这个同样同理，这个为什么这里？
哪里来的？靠什么？
啊，对，
哦，你看人家画笔好看多了。明明就是你看有内线的，它两边在展开啊。我还是那个
哦，我其实想说这个东西吧，
对啊，
是他问的是刚才这个，好像你写 C 等于 Q1
嗯
Q
嗯
我这样知道后面没有更多
嗯
intersection。就我这个是一个 algorithmic thing 哦，have something，对吧？
actually 不是这个不是这个 rank 的意思吧？你要确保这个 rank 上。
还有这个是，刚才你是用这个来看这个，
对啊，你是用下面再看上面。
这个应该是 rank，这个应该是1:1:1，我觉得。
这个就是零的。
我觉得是 linear algebra 的问题来了，对吧？为什么 rank 一个 rank of 一个 matrix 这个的话跟它的 minor 有关？
这不是他想问的问题，他想问的问题是为什么？
没有，对啊，那个问题就是 linear algebra 问题来了，就是 rank of 一个 matrix 小于等于这个的话跟那个 minor 是什么关系？然后我的 claim 应该是它是1:1的。
那为什么这个曲线就是这个 rank 小于等于？
什么意思？
这边怎样 imply 到这个东西？
哦，你是讲这个去这个啊？
对，因为刚才你教的时候，我的理解是你这边 imply 这个，这个 imply 这个，
对，
而且你说这边下来，
这两个应该是1:1，
那
不是 linear algebra。
如果这边，
但是
这一个去这一个，
如果你
这个是
如果你讲这边 if 这个 then 这个 then 我就会问为什么这个 imply 这个？
或者这个为什么 imply 这个呢？
对，
也可以吗？这个两个1:1也可以吗？
对他来讲，这个1:1，因为他这个100就在100，
对，
但是这个的话要讲100。
这一个讲 imply 这一个咯，不然这样想，这个比较容易想嘛。
对，就是他想问
第一个是它 OK，所以你是说来
为什么只有这三个？
为什么这三个就够了，不会有更多的？
对，我想一下啊，
可能是用电脑算出来。
没有，不需要，
就这边，我想知道这三个 equation 会 satisfy，就有这些 solution，只有这三个。
这个有4个答案嘛，对不对？有4个答案，现在有3个 equation，4个 variable，
Yeah，
4个 variable， 3个 equation，
不然一这条线。
4个 variable 4个 variable 3个 equation。
因为你可以看成是 T 零层这样子的东西，是 T 一层一样的东西，这样子一样的。我其实还没想出来
什么？对，他的意思是说，like 为什么这3个足够形容这个 variety 啊？
对因为你其实这子我看前面3个它是 T 零乘 T 零 square，然后 T 零乘T 零 T 一 T0乘 T1 square 啊，然后我后面3个其实是 T1乘一样的三个就是 T0 square T0 T1 T1 square，所以我等于是把它降一个 grid， 然后降成2个东西，就是它可以是 T0 跟 T1 的关系嘛，但是这个 S0 S1 S2是要设计出来这个 T0 square T0 T1 square。
还有一个重点
所以是你把 T0拉出来过后，这边 T0拉不出来。
后面前3个可以拉 T0，后3个可以拉，然后拉出来，剩下那个东西是一样。
剩下的东西，
因为我前面3个拉出来 T0，我会拿到 T0 square T0 T1 square 嘛，然后后面3个拉 T1，我也是拿到 T0 square T0 T1，
然后就这样。
它这辆是小一点，因为它上面跟下面的比较是 T0 比 T1。
然后为什么用3个就够了？
没有，你看那个东西是，它这个东西是很好的，它一3消失了。
有啊，S3在这里啊，S3都在左边。
我记得
typo，没有他 typo， 但是他好像有在 hint 一些东西的，其实他有 typo， 但是他好像有在 hint 一些东西，他好像是在看不一啊，我不是讲掉，我不确定。
但我觉得是
我不觉得是纯 typo， 他应该在想一些东西。Okay. So there's a very good question just now. So regarding the 2 examples, why these are enough equation to define these projective variety here. So I didn't argue for you for that part. What I argued just now was this equation, these. Let me. So what I argued just now is this coordinate here will satisfy some polynomial equation. Okay, but why is it enough? Okay, actually, you need some more argument. Actually, let's see that if I got chance, I will put it in the tutorial. But you can think about it. Why is it enough? Okay, for example, you might think that maybe it's enough already, and maybe you can stop here. But I gave you an example just now, right? It's not enough to just stop at 1. Okay, this is a bit like, how to say, this is a bit like your linear algebra, right? You have to solve for the solution. Okay, maybe 4 variable 1 equation. Then what's the possibility? 4 variable 1 equation. You can and if you have a solution, right? You will have what's the possibility? Your null space largest is 2, 3 dimension. Your null space, the largest null space is 3 dimension. What does that mean? So meaning you have at most 3 degree of freedom, right? Okay, so if you have more equation, then your degree of freedom become less and less and less. Okay, so in this case here, what did you see here? You have 4 variable, right, with 3 equations here. We have 4 variable and 3 equation here. So your null space is at most 1. Okay, your null space is at most 1. And in this case here, I think there's nothing in the null space, I guess. True or not? Oh, the null space is 1, right? Then it's very good, right? This is actually a line, right? This is a line. Is this a line? Yeah, I didn't draw to you. This is a line, I think. Okay, so for example, this case, this is actually a surface. I draw just now, right? This is a surface. So this is a 4 variable with 3 equation here. Sorry, 1 equation here. So the degree of freedom is at most 3 and most 3, and then because this is the projective space, so the 3-dimensional will reduce to a surface. Yeah, so it mesh out. So it mesh out with the dimension, but the problem here still is the problem. How do you decide this is the only equation is satisfied? Yeah, and think about it first. Yeah, if I can find anything, I'll let you know. Yeah, that's fine. Yeah. If you find anything, you can let me know also, or let us know. Okay, I haven't argued to you why this is enough, yeah, but I draw some picture for you to see. Okay, any other question? Actually, this is a pretty important question. I given you a parameterization. How do you decide how many equations you need? This is pretty important. From this number of equations, right, you can somehow guess already what's the object you get. Yeah, what's the object you get? Okay. All right. Let's continue first. I'll try and find, and then I'll let you know again. Have you found it first, and let me know. Okay. Definition. Now we're going to define what the homogeneous ideal is. So a homogeneous ideal in a graded ring S is actually an ideal which satisfies the following. So you can write your I as a direct sum of the intersection of Y with XT. Okay, so I don't write out the definition of intersection again. So you should apply the previous intersection. Sorry, I don't write down the direct sum definition again. Is what we had on the polynomial also. So meaning this homogeneous part, right? Okay, their intersection should be just 0. Yeah, and then when you multiply element in this homogeneous part, right, you should go to a higher graded part. Okay, with D plus E. Okay, so the graded ideal, the ideal here is kind of graded, okay, in this sense here. Okay, so in other words, an ideal I is homogeneous if only if every element having I has a unique composition. Okay, so the result of intersection being 0 is you will have this unique decomposition here because you cannot get different homogeneous part. Okay? You cannot get part from different homogeneous graded pieces. Of degree Di. Okay, does it make sense? Okay, so every element in I can split into a unique decomposition, like what we did for the polynomial. Okay, so this is the lemma we have here. So for an ideal I in a graded ring, okay, so when we say we have a graded ring, right? So every element should be able to write into a unique decomposition of homogeneous degree. Okay, and then we'll say that the ideal I is homogeneous. Okay, if and only if it can be generated by homogeneous elements. Second, if I is homogeneous, then I is prime. If and only if for any, so if and only for any pair of homogeneous element. Fg in S, we have Fg in I, if and only if F in I or G in I. Last one is sum, product, intersection, and radical of the homogeneous ideal are also homogeneous. Moreover, actually, they are just also ideal. Okay, so homogeneous ideal behave well under the operation we had on our ideal of set of points. Okay, so can anyone tell me, this is a discrete math question, how to understand statement 2 here? You, if, then only if, you, if, then only if. Maybe can we check on Eugene? Eugene, how do we split this sentence here? Oh, if I ask you to prove this sentence, what you really need to assume here? Sorry? I is prime. So wait, can you how to say? Can you tell me what is the assumption? What's the statement you want to prove? So which, okay, let me tell you let me ask you a question which if and only if is important than the other? Which one is the larger than only if that you want to? The bottom one. Actually, it's not. Actually, it's not. Actually, this is the key part here. This is where you need to split your statement. Your P is this, and then your Q is this. So this part is P, this one is Q. So inside your Q got the if and only. Okay, we will talk about it later, but this is the bigger picture first. Okay, and then this is the extra thing. This is the extra thing for this if and only if to works. Does it make sense? If I can, maybe I can put like this. Suppose this is I is homogeneous and then comma. I mean full stop. Okay, then I is prime if and only if this happens. Okay, so another question. So since Q have a if and only if, so for the first if and only if, right, you need to show P to Q, Q to P, right? Okay, so from Q to P is okay lah. You just show that I is prime, but P to Q, then what you need to do for Q? You need to show that if and only if. Okay, you need to start with this any pair of homogeneous equation and then do this two direction here. With what assumption you can use if you want to prove Q? How many assumptions you have? 2, right? Okay, one is coming from I is homogeneous, the other is coming from I is prime. Okay, this is for P implies Q. Okay, make sense? Do you have idea already? Okay, how to understand this statement? Yeah. Okay. All right. The other is kind of straightforward. Okay, good. Okay, so let's talk about proving them then. Should I argue why Eugene? Should I argue why this one won't work? Do you understand why this won't work? If you just look at this, if you want to prove this statement, right, then what's the other statement trying to do? Then doesn't make sense already. So this is how you think whether your split is making sense or not. Does it make sense? Okay, because if you are trying just to prove this if only, then the previous if only is like, not sure what's that already. Okay, but if I split at the first if only, then it makes sense. This the if only in the Q part here will be a standalone statement. Okay. Okay. Right. So for the first one, which direction is obvious? What's the ideal being homogeneous? You can write it as a unique decomposition. Again, in a different level. So what's which part is obvious? Right to left, right. Because if your generator are already homogeneous element, right? Then no matter how you multiply, you add, they are still in a homogeneous part. But the problem is the other direction. If your ideal is homogeneous, okay, how do you show that the generator are also homogeneous? You know what does it mean by homogeneous elements here? So here, for example, e.g., you might think of like x squared plus y squared. Okay, this is homogeneous. But what is not homogeneous here? Maybe x plus y squared is not homogeneous already. Okay. So if you know that your generator is already homogeneous, then no matter how you multiply, then you still keep your homogeneity. But if you know that your ideal is homogeneous, can your generator be non-homogeneous or not? Can or not? So if your ideal is homogeneous, can it be generated by non-homogeneous element? Suppose you have a non-homogeneous element in your ideal, right? Then that's the element that you cannot write it as. Oh, you understand? You understand? Huh? Huh? Jinsen, what are you thinking? Huh? 对，什么？难道这里有什么的？啊啊，不是很懂，可以从头解释一下啊？没有，我就想问你吧，对这句话是什么理解？What do you understand about this statement？啊啊呀啊，在上面一点啊，上面一点，哪里？嗯哼，解释呀，解释。可以 try 一会儿呢，因为发现听不懂。嗯哼，嗯哼，Can we integrate that？上面呢？嗯哼，sure。Then how does it answer this? How does it prove this statement here? You don't know. So which direction you think is easier to prove? Huh? Backward direction. Okay. So how do you prove? If you have if it can be generated by homogeneous element, why is it homogeneous? Follow from definition. So can you tell us? So if it can be generated by homogeneous element, then why is it? What's the definition? So in other words, I'm asking what's the definition of homogeneous, I think. Huh? Yeah, I'm asking you.
Yes.
Yes. Huh? Yeah, can you tell us? Previous。我跟你讲，我工作也是这样，很生气的时候遇到这些同事，那个你去看，不是很好感觉啊？I plus what? Direct sum. Direct sum. Of what? 啊？ And then? Okay, so you tell me definition already. You haven't tell me how to understand the definition. Huh? You good, you do the first step, okay? You tell me a definition. Now you need to tell me how to fulfill this definition. Okay, good. You read me another equivalent definition. So how to use it? If my ID already generated by homogeneous element, how it fulfill that definition? Yeah. So what does it mean by generated by homogeneous element mean? Yeah. So what do you have in your generation? Okay. So what's AB? Product. Okay, so you get product of homogeneous element, right? But those will live in another graded part, right? Okay. And then you add them together, they also live in the same graded part. Yes. Okay. Sorry. What do you mean? What do I mean by graded part? Ne? Is what you say. I intersect with XD. They are living in a different. So okay. Oh, this part here. This part. They are living in a different graded part. Fine, okay. Yeah, so if you have like homogeneous elements, right, it must be in of some degree, right? So if you have different degree, multiply them together, they still live in the same homogeneous degree part. Okay. Yeah. Okay. How about the other direction? Huh? Huh? Uh-huh. You just say. Hmm. Mm-hmm.
I do this
Okay. I think that's a very clever way. Okay, because your eye is already homogeneous, right? Okay, then you can split it into this homogeneous part, and then you just play a lump sum game, so just Just use these. Just use the summand to become your generator. Yeah. And then these are homogeneous elements. Yeah, I think, yeah, very good. Good. Yeah. Actually, this lemma is supposedly to be not hard. It's like that one. It's just trying to dissect this definition for you. Yeah, I think quite good. Yeah. Any easier way? Yeah, good. Yeah, because there's no restriction here, it doesn't say that, oh, you need to find one or something like that. No, never mind. So you just take everything you want, okay, anything you like. Okay, how about second one? Okay, I think second one is more obvious lah. But what's the subtlety here? Prime says what? If FG in I, F in I or G in I, right? Okay, but here they reduce it to homogeneous element pair. Okay, so in I, right, maybe you don't have homogeneous element adding together because maybe come from different homogeneous part. But this statement tells you that you just need to check for the homogeneous element is enough already. If all the homogeneous elements satisfy this prime property, then the whole ideal, homogeneous ideal will be. Does it make sense or not? Does it make sense? Because in your ideal, maybe there's something like this. Okay, but it's enough just to check x and y squared is enough. Okay, this is what this what this what these statement trying to do. Okay, does it make sense? Do you know what this statement trying to say? Without even proving it, you should know what this statement doing. Okay, even without proving it. 很多 there's a lot of misconception by student. They'll say, oh, I can learn proof first, and then I will understand the statement better. This is true for maybe from my experience, 40%. You almost cannot learn from proof if you don't understand your statement. Because you don't know what you are proving it. You think you will know after you're reading the proof. Proof is even longer than the statement, you know. So it means what? You are trying to make your word even harder. 你没事找事做 you know. So the statement is served without proving, from my experience, you must understand first. Without proving, you already need to know what this statement is trying to do already. Okay? So this statement is trying to say, if you want to check whether an ideal is a prime or not, you don't need to check random two elements. You just need to check random two homogeneous elements. Yeah. Does it make sense? Okay. This is a very good exercise that you can try. 3 actually, most of it is trivial, except radical part. And most of it is just trivial because you add your product is respect by your grading. But how about radical? Okay, radical part is non-trivial a bit. Okay, so what does it mean by radical of a homogeneous ideal is a homogeneous ideal? Well, radical of an ideal is still an ideal, right? Okay, because homogeneous ideal is another ideal, so you cannot go other way. But the point is, why is it still homogeneous? Okay, why is it still homogeneous? Okay, to prove homogeneous means what? So what is the radical of homogeneous ideal here? Radical of homogeneous ideal here meaning what? If we understand the element of the radical ideal as a root, right? So if you take n root of the element of homogeneous ideal, why do you expect that? Why do you expect that it is also can be written as homogeneous component? Why do you expect that? Okay. So not just living in homogeneous radical, right? Ideal, right? which homogeneous ideal is referring to? You have to lift back into the radical. Okay. You have to go back to the radical. Right, so this is the hard part here. Okay, so why the end root of this element here, if you write it as homogeneous part, why this homogeneous part also live inside the ideal? Right. So you are not just living in the greater part. You need to live back inside the ideal also. Okay, so in this case here, we replace here with square root I. So why if you write your square root I in terms of homogeneous degree, right? Why the part also live inside square root I? This is the hard part here. Okay, can everyone understand what's the technical problem here? Okay, so for every square root I elements, right, you already split into homogeneous degree D, but why the part also live inside square root I? So again, you need to show to some power is living inside I for those pieces. This is the hard part of it. Okay, so let's quickly do it. Okay, I try to fill out Adrian gaps here. You wait, nothing to show down. OK， 对哦，讲到这个，你们还没有 post 出来的，我们课都要上完了，你们的那个 note seminar 的 note， 我们课都要上完了。
哎，我的好了，那我。
OK， let's check. Okay, so what we're gonna do is okay, not two direction here, just one direction here. So we'll try that. We'll try and show that the radical homogeneous ideal are homogeneous. Okay, so what we do is let's pick an R in I such that Rn in I, anyway, this is in square root I. Okay, then suppose that R can be written in the direct sum of a homogeneous part, right? So now our problem is to show that all these homogeneous part live inside square root I. So this kind of statement, right? Okay, so let's write down here. I want to show that all Ri live in square root I. So you can see that this statement will hold for all k, right? So this is hinting some induction. Okay, let's say you don't have so many pieces, you just have one piece, R naught. Then R is the thing inside radical. Then R naught must be inside radical. So we can apply induction here. Okay, so we can assume that, maybe we know that the first k plus 1 is living inside a radical. How do I prove the last one? Okay, so by induction, actually we just need to care about whether we can show that. So it suffices prove that the largest one, Rk, is in the radical. Okay, this is induction. So if k is 0, we already show that R is inside radical by assumption. So try induction. But if you expand this R, what happened? You use the same n that makes sure that you lie inside the power that makes sure you lie inside the homogeneous ideal. So you expand this, then we can note that actually Rnk is the only part of degree nk. No other will have degree nk because other should have lower degree, right? Right. This is how, at least this is how we rearrange our homogeneous degree. It's small to big now. Okay. So if you try to expand out, right, this is the highest degree. Actually, this is not too directly because you need to consider cross term also, right? But I think this is a combinatoric problem. Yeah. Who don't care? What do you mean? Yeah. So my point is, when you argue that there's only one part that give you this high degree is from a combinatorics argument. When you do the cross term, they won't give you the highest degree. Okay. But we know that this Rn, right, is living inside the homogeneous uh, idea, right? This means what? This Rnk here, so Rnk here will live inside I intercept Xn. Right? Huh? Sn. Sn. Oh, thank you. Snk. Thank you. Yeah. Okay. So this implies that Rk also live in square root I. In fact, it lives inside square root I intercept. Okay, does that make sense? Okay. I guess then for the previous term, you just use induction. Okay. So we have 3 more minutes. Okay. In this 3 more minutes, I don't want to throw you all a new concept yet, but I want to tell you what's coming up for tomorrow. Maybe you can speak faster. So the other thing is you can show that Vt equals to V of ideal generated by T. This is similar to R5 case. Okay, you just don't look at the zero of function. It's equivalent to look at the zero of ideal generated by the function. It's the same. So similar for this homogeneous generator case. And then we will have the Zariski topology also. Okay. So this Zariski topology is talking about projective algebraic set instead of affine algebraic set. Actually, if you learn subspace topology also, we can deduce that actually, not subspace, sorry, it's a quotient topology. Okay, so which one is a quotient topology of which one? Projective variety is a quotient topology of Zariski topology on alpha. Maybe I'll put this in the lesson. Okay. Yeah. So this kind of formulation is very similar to affine setting. Okay, it's really the same. Just you add in the adjective of projective. That's all. Okay. So that's why people will talk about algebraic set in general. Okay, because they really have the same property. So sometimes you need to ask whether it's affine or not, whether it's projective or not. Later I'll tell you how to go between them. Okay. Another way to understand Zariski topology is quotient topology, just now I mentioned to you. And then we can define what's a projective variety. It's irreducible projective algebraic set. Once we have topology, right, we can talk about irreducibility. Okay. And then what's a quasi-projective variety? Is an open subset of a projective variety. So last time, Justin asked a very good question here. So quasi-projective variety here, should it be irreducible or not? Might not be. I don't know why they use this terminology of variety, but at least from what I read in their book is they don't imply it, because sometimes they talk about reducible one, sometimes they talk about reducible one. So in this class, right, we will make sure that we will say irreducible quasi-projective variety to mention that it is irreducible. Okay. And then we'll talk about projective Hilbert noun standard. Now here, what's the left-right correspondent here? One side is homogeneous ideal, the other side is projective algebraic set. Okay, and this very interesting ideal here called the irrelevant ideal. Irrelevant ideal means what? 华语讲没有用啊 ，useless. Why is it useless? What's the zero set of this ideal? Zero. Do our set have zero on our projective space? 我们有零，没有。Yeah. So this is useless ideal. Okay, so it defines an empty set. Okay. So this is slightly different from R5 case already. R5 case, the ideal that give you empty set is what? The whole thing, but here got an irrelevant ideal. This is not the whole space. So the remark here is you can make out all the D plus the pieces that greater than D, D equals to 1. Okay, this ideal here will make out this proper subset of your polynomial ring. Okay, all the D plus D greater or equal to plus 1 pieces. Okay, you just cannot make out the constant. Okay. Okay, so how do we go between it? We will use something called affine cone to go between it. Actually, it's the origin, the 0 is the key point here. Okay, you just need from the example I gave you just now, right? You can easily regard these. Where is it? So if you look at the example I gave you just now, so give me 2 more minutes. So if you regard the example I gave you just now, you can just easily see this. Okay, at least this one. This equation here in affine setting, why not? It's perfectly fine. It's perfectly fine. Okay, but if you look at in the affine setting, right, you'll find out that there's extra point is satisfied, which is all 0. This is true for all homogeneous polynomial. Okay, so actually the 0 set on projective case and affine case, the difference is what? If you get a 0 set of projective variety, you just add 1 0 in, then you get the affine picture. So this is how you go between these two. Okay. Okay. So see you tomorrow.